project or theory or both? Both? Okay. So why don't you ask now? Just for interest sake. Because I'm not going to say, I'm going to ask you what must I repeat. But okay, we're going to do it the third period. Right. Okay, so let's try and see whether we can get through this. I actually prepared a double lecture where I can go through everything quickly, but so now we can just do a little bit. Remember what we've done. In section 3.1, we said, hey, looky, let's make objects. Objects are cool. And then we had a look at if I give you an API, yes, for a certain class, which is the implementation of the object, we looked at how do I call this API. So I write my own little Java program as always, and I can now use the objects. How do I use the objects? Yes. Then in section 3.2, we said, okay, now I know how to use the objects, but I want to write my own objects. Yes, I want to make my own class containing objects. How do we do that? And we had to look at the Java, how to do that. And now is the bummer in 3.3. That's all very well, but we looked at the in 3.2 at the specific Java syntax of doing things. But when I do my project or when I do my own implementation, there are certain decisions that I have to make. How do I implement objects? What is the right way of doing it? So those are design decisions. I got an email last night saying, oh, I want to make an object which is a car, and I think it has to have colors and stuff, but I don't know how to implement it. So one thing, the question actually beneath all that, because implement, if I know everything about the object, it's easy to write the Java. But making that decision, what properties belong to an object? Must that, what methods must be public? What methods must be final? All those things. And that is what, those decisions is what we cover in 3.3. Right? There are three things that we are going to look at. The one we looked at on Monday was encapsulation. And the idea is it's really silly using objects if you don't protect the information in the object, in the class file, where you implement the object, because that's the whole point. Objects is supposed to make programming safer. Okay? So we're going to look at encapsulation, immutability. Well, yes, you know, see last year and my copy. What's the third one? Inheritance. Thank you so much. Okay? Right. So Monday we covered encapsulation. Encapsulation is simply protecting my instance variables. What does that mean? I encapsulate that. I put a cap on the variables. The client code cannot directly access the variables. For example, if I did not have private there, ignore the final for the moment, if I didn't have private there, any of the client code could have said complex.r and changed the variable. That is not good. If you want to give values to an object, you can't just willy-nilly allow everybody to do, any client to do that, because then it can cause chaos. Okay? So that is the encapsulation, the private keyword in Java. And that means that only by using the API in a structured manner can I say change values. Okay? Right? That's encapsulation. The other one that we want to look at is immutability. Now, we talked about immutability when we did complex numbers. And there was this very strange thing that when I write the code to implement objects for complex numbers, we said that a complex number can get a value once at instantiation, and the value can never change. Right? And that sort of feels counterintuitive the way you're using variables at the moment. So one has to make that mental leap about the difference between an object and a variable. Because we use the primitive types, and then, you know, the whole thing about a variable of a primitive type is that it is variable. It keeps on changing its values. With objects, that is not necessarily a good idea. There are some cases where we want to change values and some cases where we don't want to. Right? And complex numbers was the one case where we said, I will allow this thing to change its values. The other one was string. And you think that strings have to keep on getting new values because I'm working with my strings, right? Not necessarily. So this is the practice that you have to get in object-oriented programming. When do I make something immutable? Immutable meaning I can never change its value after instantiation. Okay. And when not? I found personally that if I get these kinds of new concepts, read a lot of programs. So there are programs in the book, but that's not enough. So go out there, read code, good, bad, ugly, beautiful. Read code and ask yourself, why did these people do it this way? So take any job. There are hundreds of online tutorials on Java. So look at it. See what they say about immutability. When do I make something mutable? When do I make something not immutable? So, for example, I'm going to confuse you all about your project now. The car. Clearly, a car in the project is an object. It's got a color, it's red or not. It's got a position initially. It's got a width and a height. So the width and the height and the color would never change. That must be immutable. But the position must change. Is that a good thing or not? What if the client code can change my position by getting into my class code? I don't want that. So there must be an instance method that can change values as far as position is concerned. Or, so you have to look at all the examples in the book, yes? And make sure whether the whole object is immutable or not. Yes, so that's a design decision. You have, in the TUTs, you have to talk to the demo. It's too late now already for the project, but I got, again, the famous email of last night. I got a couple of questions on the project, and I said, well, did you ask in the TUT? Because I explicitly told all the demos, ignore the TUT questions for a while, ask them about the project, ask whether there are any questions on the project, let them ask questions about the project, answer them. So that specific email, no, they didn't ask in the TUT yesterday. That's what the demos are for. So, okay. Immutable cannot change. And here are then a few examples. That charge thing, that makes sense, that it must be immutable because it's a point in the Cartesian space and it sticks there. You know, a charge at the position x, y stays what it is. It never changes. It's a constant. Color, Well, I don't want my colors to willy-nilly change. If I have bright neon red, it must stay bright neon red. It cannot suddenly become something else. Stopwatch, we didn't talk about that very much. Complex and strings are the things that should worry you a bit. It's a bit counterintuitive about this. Over here we have examples of things that can change. Now the turtle is the one probably relating a bit to your project. Remember, the turtle was, I have a position and an angle, and now I can move a certain number of steps, and then it draws these little figures, right? So turtle is mutable because the turtle must be able to move around. Okay, right. Mutable types, Now, the good, the bad, and the ugly. What are the advantages of immutability? Well, immutability allows me safe programming. Why do I say that? Because I know the client code cannot bugger up my values, to put it mildly. Yes? So if I have a bug in my program, either the bug is in the object instance methods, yes, something goes wrong. If my object gets the wrong value somehow, the bug must be inside those 5 or 6 methods in my implementation of my object, because the client code cannot access it, cannot change it. So private final is the thing. If your object gets the wrong value somewhere, and there's a bug, you first go to your object Java file and you see, oops, did I remember to put final there? Okay, because if it is final, then the client code cannot mix up the values. And if it is final in the private final and the client code still manages to mix up the values, well, it can't be the client code, so then it must be in these 4 or 5 methods. That's the implementation. Okay? Right? Okay. But what does it cost me? The cost of immutability is that I must create a new object for every value. Remember, with complex numbers, basically you have, if I have a complex number with a certain value, I must create an object for it. So I'm going to have a whole set of objects. And inside that set is every single complex number that I want to use. Okay? Depending on your specific application, oftentimes it's better to be safe than to try and save memory. Okay? Because you know that computers actually have a hell of a lot of memory these days, depending on the application, right? So for example, in your project, my word, how big can the grid be? How many cars can it be? I'm not going to have 10 million objects in your project. I promise, there's not a file that big. So if it's small, then it doesn't matter that I'm wasting that space. Okay? Because the advantage of being safe and being able to trace my bugs outweighs the extra resources that I use. In the old days, when I was a young and eager programmer, we used to work on mainframes and mini computers. I actually did my degree before PCs were there. Right? Unbelievable, but it is so. And resources were an issue because resources were scarce. Yes. CPU, we worked on a quota system on the mainframe. And if your program is very inefficient, and you use up your quota before you manage to hand in your stuff, well, and you bugger, then you have to go and pay physical money to get extra quota. Okay, so you didn't want to waste CPU cycles, and so on and so forth. But nowadays, resources are so cheap. Okay? You have to be aware of exponential explosions, because then the program simply will never finish. Yes? But in general, programming safely is better than trying to program efficiently. Yes, unless you have a very weird problem that is known to be NP complete. Okay, right. So the cost of immutability, don't worry. I've had students who said, but well, I don't want to call a method because there's an overhead attached to calling methods. I'd rather just write. How silly. 30 years ago it was an issue. Today it's not an issue. Okay. Right. Okay. Now, if I declare a variable as final, let's look at code, max count over there, private final max count. Private, it's encapsulated. Final, it's immutable. Yes, so the client code cannot read, cannot change it. Okay. However, what if I do this? Private final, double array of coordinates. Oh, we're implementing vectors as an example, but okay. What if I have a reference type which I make private final? And I had this question when we were doing 3.1 from somebody, I can't remember who. Okay, yeah. What is this safe? Can the client now change any of the coord's values? Yes, it can. Why? What does this declaration do? It makes the reference private and final. The reference. Yes, because this is a reference I'm declaring here. So I make the reference private and final. But the client code can still be clever and get to the values. Okay, so I'm only making the reference private and final, which is a problem. So here is an example of how it might work. Suppose I have that in my public class vector. A vector is an array of coordinates. Right? So I make it private and final, and I'm happy because now it's encapsulated, it's immutable. Not. There's an implementation of vector. It gets an array, puts the values in there. This is the constructor, right? Okay. So look at this client code. I declare an array A of doubles. I give it values. I instantiate a variable of type vector, an object. And now I do this. A of 0 is 17. Oops. Yes, I got, although I cannot change the reference, the pointer pointing to that value, yes, I cannot change this value. But if I have this value, I can merely change, if I have that reference, I can merely change the values where that reference is pointing to. And so again, a bit of overhead. What we're going to do, yes, what we're going to do is we make a defensive copy. And defensive copy means that the class itself, the constructor, I have my private final. There's no other way I can do this inside the object code. I make my reference private final. Yes. But then when I instantiate, I make a defensive copy of the values. What does this mean? Well, I get my parameter a in, yes, which is of type vector. And then I literally copy these values into quotes. Yeah. So I have a defensive copy. I make an extra copy, as it were. Yes. And now the client can't get that. To see this, I need you to do it. So what I want you to do is go to the computer and take this vector program, yes, do the client code as over here, do the client code and print the values, yes, so that you can see, okay, cool, it's working. Then try to overwrite, again print the values of that object, yes. Change this code not to be defensive. Okay, so there are two versions of the constructor. It's this version, which makes a defensive copy, and it's this version, which does not. Yes? You can see what this does. This simply copies the reference. Yes? It doesn't look at the values where that reference is pointing to. This version physically copies the values of A, right? And see, when you have these two different versions, draw the memory on a piece of paper. You have to learn that for the test anyway. Draw the memory and see what does what. Break the code, right? Different versions of the code. Yes? Is that okay? Good. So the principle is the following. Immutable means I write the keyword final. Yippee! My stuff is immutable. The values can never change. If and only if that variable that I'm making immutable is a primitive type. If that variable is a reference type, it's making the reference immutable. Okay? Which means that the client code, if it has that reference, it can still change the values that the reference is pointing to. So that is not safe. So how do I guard against that? In my constructor, make a copy of the values. Okay, so that I have a defensive copy that the client cannot change. Okay? Right? Okay. But you have to, I find that first year see this for the first time and it doesn't make sense to me. Well, to them, sorry. You cannot see how this safeguard. And the more I say that this is a defensive copy and now the client can't change the values, it just doesn't make sense. So I need you to jump on the computer and I need you to play with this until it makes sense to you. Okay? It's like riding a bicycle. I can explain and explain and explain and explain how you must keep your balance, but until you've tried it, it's just words. So go and play with this, okay? See that it actually works or not. Okay. So the example in the book is about vectors. I'm simply going to say that a vector is an array of coordinates, and then you can plus, minus, times, dot, magnitude, direction, whatever. Yes? The API for vectors. How many of you are doing econ? So you're not necessarily familiar with vectors, or did you do it in maths in school? Do you know what a vector is? Yeah, okay, cool. So I don't need to talk about it more, okay? So these are the kinds of operations we used to. I'm sending a vector B, and I want to add it to, say, vector A. So in my client code, I would say A dot plus and send over B. Yes, and that would A plus B for me. There are other instance methods in my API. For example, I want to know what is the direction of a certain vector. Now, the book doesn't give the client code, and I think it's a very good thing that it doesn't. How would I use direction? Remember that I have an object. Say I have a vector A, yes, and I'm using my API and my standard Java syntax. I would say A dot direction, yes, because I want to know what is the direction of this vector. Yes? Does this make sense to you? Because this is how we use objects. We say, this is my object, what is its direction? Oops, because now we get into our code, which implements direction, and this is a problem because, this more clear. If you look at this, there's no parameter. Oh my word. So how does the instance method know which object I'm talking about? And in such cases, we use the keyword this. And this means the object with which the instance method was called. So you can think about it. There are cases where we don't send over the parameter. So this is our client code A.direction. But how do I implement the instance method then? So the object has to know which object called my instance method. Yes? And over here then, this would be compiled and executed with return A dot times, if you see what I mean. If I call it with A dot direction, then this class would know that the keyword this must be replaced by A. Okay, but I can call it with many vectors. I can call it with A or B or C or X or Y or whatever. Okay, so this is a general keyword which says that object with which this instance method was called. And then we use the Java this. Okay. There are different styles and different preferences. Some programmers like to this all over the place. Okay? The book argues for use this sparingly, the keyword this. So read their arguments, see what they say, make a decision on what your style would be. Okay? That will be very different. You'll see different implementations where this is all over the place. You'll see other implementations where it's used here and there. Okay. Right. So that is what this means. It's sort of a communication. We have the object implementation and we have the client code. And normally, the client knows the names of the object and call the operations, but it's seldom that the object implementation must know something about the client code. So this is sort of a communication in the other direction. Yes? So if I have an operation which can be applied to very many different objects of this type, and I don't know what their names would be I'll use this. Go play with it. Okay? Get it? Right. And now we get to something which to my mind, I probably shouldn't say that. You mustn't be negative when you talk about your textbook. But I find the description of inheritance difficult to follow in the book because they don't give enough examples. Okay? But it's a very important concept in object-oriented programming. But our examples are very simple at the moment, they're very small, so it's sort of difficult to illustrate this. Let me tell you that from page 434 up to 446, there's only one definitional question in the test paper. Okay, so if you now become confused, you have to sort out the confusion, but it won't have to be before next Thursday. Okay, there's one definition question there. I think it's 2 marks out of 25, which is a lot anyway. It's 8%, but okay. So learn your definitions. If you're totally confused, learn your definitions about inheritance. Okay, and then live with it, because as you get more and more experience and practice in object-oriented programming, it will start to make more sense. Okay? Right. So I'm going to stop now. On Monday, we're going to start with inheritance. Let me just leave this with you. You don't want to reinvent the wheel. So there are some functionality that you want to share between unrelated objects. And that is what we call an interface, and then you can inherit certain properties, so you can make classes of things stacked hierarchically to inherit certain properties. But we'll tackle that on Monday. Okay? Third period in the computer science lecture room, anybody who needs any discussion of any kind whatsoever. However, if you walk in there and I don't get questions, I walk out again. You have to at least be prepared to ask me questions, please. Okay, great. Mike.
In the development of word, can I use objects